Good morning, everyone. My name is Arjun Venkatesan. I'm one of the Associate Director at the New York State Center for Clean Water Technology. Thank you for joining us today for the Center's seminar series, and wish you all a very happy New Year. And I'm going to kick off the seminar series this year with a presentation on the treatment of per and polyfluoroalkyl substances. It's essentially more of a literature review to understand the current knowledge and status of the treatment efficiencies of various systems in treating PFAS contaminated water. And I'd also like to highlight some of the current challenges in the treatment of PFAS as well. Quick overview of the presentation. I'll be giving a very brief introduction to PFAS and then talk a little bit more about the currently available treatment options for more specifically on the water treatment side. There are two main categories of treatment options. One is sequestration approaches that includes granular activated carbon, ion exchange treatment, and also membrane filtrations like reverse osmosis. That would be the major chunk of today's presentation because many of the studies are focused on those approaches for PFAS treatment. I would also briefly touch the available technologies for destructive removal of PFAS and highlight some of the ongoing research at the Center for Clean Water Technology, more specifically on electrochemical treatment and electron beam treatment of PFAS, and conclude my presentation with a summary of what we understand to date about PFAS treatment. So what are PFAS? Per and polyfluoroalkyl substances are man-made chemicals that contain multiple carbon-fluorine bonds in its chemical structure. Carbon-fluorine bond is one of the strongest in the universe. And as a result of these multiple carbon-fluorine bonds, these chemicals feature extreme stability and resistance to reactions. As a result, they can resist heat, oil, stain, grease, and even water. And they've been widely used since the 1940s in various commercial and industrial applications. Some of their applications are highlighted in these pictures. They're coated in food packaging materials, water-resistant clothing. One of its important applications in the past has been the Teflon coating on non-stick cookware. They also coat carpet materials to serve as a fire resistance. And one of its most important life-saving and application is in firefighting foams. Two of the very most commonly studied PFAS is shown in this figure right, which is perfluorooctanoic acid or PFOA and perfluorooctane sulfonic acid or PFOS. As you can see, they have a brush-like structure. Each of these nodes represent a carbon atom, and you can see multiple carbon-fluorine bonds in their chemical structure. And the functional groups can also vary. And for octanoic acid, it's a carboxyl functional group. And for the sulfonic acid, it's PFAS. For the PFAS molecules, it's a sulfonic acid. What we need to realize here is PFAS are not one or two chemicals, but they represent a family of chemicals. Currently, there are like more than 5,000 different organofluorine compounds that falls into the category of PFAS. And it's a very complex group of chemicals that we are still trying to understand as we do not have like ability to detect many of these chemicals in the environment. So since PFAS is widely used in various products, it's pretty much everywhere in the environment, and we get exposed to them through multiple pathways. We can breathe contaminated air, and one of the important exposure is through drinking contaminated drinking water. We can also get exposed to PFAS through coming into contact with materials that's coated with PFAS. And eating food that's contaminated with PFAS as well. So there are different ways that we can get exposed to PFAS. And there was a nationwide study that showed that more than 99% of the United States population is already exposed to PFAS. We have these molecules in our blood. PFAS, unfortunately, have been associated with a very long list of health risks, human health risks. And this figure is a very good summary of the various studies that has shown the association of health effects with regards to PFAS exposure. A solid line represents high certainty from these studies, and a hyphenated line represents that a study shows some correlations with these negative health impacts. To highlight a few of the health impacts, so exposure to PFAS has been associated with lower birth weight of babies, reduced response to vaccines, and more and a very important health effect is, of course, its association with increased cancer risk, like increased kidney cancer and testicular cancer. And as a result, one of the PFAS, perfluorooctanoic acid, or PFOA, has been classified as a possible human carcinogen by International Agency for Research on Cancer, or IARC. PFAS is a widespread contaminant in the US. This is a map from the Environmental Working Group that shows the detection of PFAS across the United States. As you can see, they're pretty much detected in every single state in the US. And some of these states, although they don't show a lot of detection, doesn't mean that PFAS do not exist. It means that the data is unavailable, or these states have not monitored some of these waters for PFAS. Unfortunately, there are no federal regulations for PFAS in drinking water. So individual US states have come up with their own regulations. And in New York State, two of the PFAS chemicals, like the PFOA and PFOS, is regulated in drinking water at 10 nanograms per liter of parts per trillion levels. And the New York State Drinking Water Quality Council is currently considering to add additional PFAS for regulation that includes short chain PFAS as well. So looking more closely in the Long Island area, there was a study conducted by the United States Geological Survey to look at the concentration of PFAS in the groundwaters in Long Island region. And they detected a concentration up to 93 nanograms per liter from different land use settings. And in some of the wells that was collected downstream of decentralized wastewater treatment plants, the concentrations were much higher, and concentration up to 620 nanograms per liter was detected in groundwater from Long Island. So now looking at the technologies, available technologies for PFAS treatment, the technologies can be categorized into two different types. Like one is sequestration technologies, the other is transformation destructive technologies. Examples of sequestration technologies can include sorption, membrane filtration, and coagulation. So your activated carbon filtration and reverse osmosis falls into this category. And what in these technologies, PFAS molecules are physically removed. So they are not essentially destroyed, but they are removed by physical sorption or filtration happening in the treatment systems. For destructive technologies, some of the examples would be electrochemical oxidation or ozonation. And the goal of these technologies is to actually transform PFAS molecules. So they break down the PFAS molecules into innocuous compounds. Although all these technologies are available, not all these processes are effective in treatment of PFAS. On the figure on the right, this is a good summary of where each of these technologies fall when comparing to efficacy for PFAS treatment and also cost associated with PFAS treatment. And as you can see, many of these technologies are not as effective in PFAS treatment, especially biological or membrane filtration, microfiltration or ultrafiltration are not effective at all for PFAS treatment. And for the treatment that are more effective, like for reverse osmosis and nanofiltration, you can see the cost for treatment is much higher compared to the other traditional water treatment approaches. Granular activated carbon shows good efficacy in PFAS treatment, and it also is economically feasible. So that's probably the most commonly used technologies for PFAS treatment of contaminated water. Out of all these technologies, the mature technology, which has been demonstrated in the field for its effectiveness for PFAS treatment, include activated carbon filtration, ion exchange resin treatment, reverse osmosis, and nanofiltration. And the majority of today's presentation are going to focus on studies that looked at full-scale evaluations of these different technologies for PFAS treatment. In addition to various different technologies, like the efficiency of the treatment processes is also going to depend on the type of PFAS you're treating, because the chemical properties of PFAS vary with different chain length, functional groups, and the degree of fluorination. For definition purposes here, we want to categorize PFAS into short chain and long chain. Short chain compounds are defined as compounds with chain length of carbon 6 or lower than 6 for sulfonic acids, and less than 8 carbon chain length for carboxylic acid. And anything greater than these numbers are considered as long chain PFAS compounds. So on this table on the right, you can see the short chain compounds are highlighted with the red box. And this is a good table to show how the properties of these short chain and long chain compounds varies. And the property here that's summarized is the octanol water partitioning coefficient, which is indicative of the hydrophobicity of the compound. So as you can see, the short chain compounds have lower value for this octanol water partitioning coefficient, meaning that they are less hydrophobic and less likely to adsorb onto your filter materials as well. So the properties of the PFAS can also vary depending on the isomer that you're looking at. So we all know that PFAS is one compound, but PFOS can exist in different structural isomer forms. So you can see the difference here is the linear form, where the carbon chain length is a straight chain length, but in the branched isomer, this change in structural isomer of PFOS can impart different properties, and it can behave differently in different treatment systems. So going on to the first treatment process, which is granular activated carbon. GAC is probably the most common technology used for PFAS treatment currently, as they are effective in treating both short chain and long chain compounds with some challenges, which we're going to discuss today. GAC material is usually made from bituminous coal or coconut shells, and they feature very high porosity, and as a result, they have large surface area, which provides additional sites for PFAS to adsorb onto. Activated carbon can come in different sizes. They can be powder material, in which case they are called as powder activated carbon, and then they could also be granular, which is GAC, and also in pellet forms. The main mechanism by which PFAS is removed by GAC is through hydrophobic interactions. That's the dominant mechanism. So as we already discussed in the previous table, the long chain compounds are more hydrophobic and more efficiently removed by GAC, whereas short chain compounds that feature less hydrophobicity are not as effectively removed by granular activated carbon filtration approach. This is a visual representation of how PFAS molecules are removed by GAC. It could be through charge interactions. Some of the granular activated carbon can have like positive charges on their surface, and PFAS are anions, or negatively charged ions, that can interact with these positive charges. And that could be an additional way of retention in these filtrations approach. But however, hydrophobic interaction is the important mechanism for treatment of PFAS using GAC. The other most commonly used treatment approach for PFAS is anion exchange resin treatment. Anion exchange resin works in two ways. It can have the same hydrophobic interaction as described by granular activated carbon filtration, but in addition to that, electrostatic interaction also is important for PFAS removal when using ion exchange resin. As an example, to differentiate these two mechanisms, let's look at the example of PFOS molecule. The long carbon fluorine tail provides the hydrophobicity for this compound, and that interacts with the adsorption that imparts hydrophobic interaction with the ion exchange resin, whereas the charged functional group, in this case is a sulfonic acid with a negative charge, that can interact with the positive charges on the ion exchange resin material. The figure below here shows how the ion exchange resin works. Ion exchange, as the name suggests, the PFAS molecules is exchanged with another anion that's present in an ion exchange resin. And in this case, example, chloride is the other anion that's released back into the water in exchange for PFAS absorption. Ion exchange resin can be single-use versus regenerable resins. Single-use resins typically show better performance than regenerable resins, but they are just used one time until exhaustion, and after treatment, they are being discarded, either incinerated or sent to landfills. Clearly, there are some advantages for ion exchange treatment over granular activated carbon filtration, as they exhibit faster reaction kinetics. They show higher operating capacity, and they are extremely good for treating highly concentrated PFAS waste streams as well. So I would like to start with some definitions, because when I go through and summarize some of the existing studies for the treatment of PFAS, these are some terminologies that I would commonly use. The first one is empty bed contact time. This is essentially the amount of time the water spends in contact with your filter material. So for example, for a fixed volume of carbon, a granular activated carbon bed, a low flow rate would indicate a high empty bed contact time, and vice versa. The other terminology that I would use in comparing the treatment systems for the removal of PFAS is the breakthrough. Breakthrough is essentially defined as the occurrence of PFAS in the treated effluent due to exhaustion of the adsorbent. And the breakthrough could be defined by at what level you actually see this breakthrough happening. And this is explained really well in this curve below. The breakthrough curve is essentially plotted as C over C naught, which is a ratio of the concentration in the effluent over the initial concentration of PFAS in the untreated water, plotted against the bed volume, the amount of volume treated by your reactor. So when we start with the fresh carbon, you essentially do not have any PFAS coming out in your treated effluent. But once the carbon is being exhausted, the concentration of your PFAS in the effluent starts to increase. And the breakthrough is defined as usually by the treatment goal, either 10% of the initial concentration or the 50% of the initial concentration occurring in the treated effluent. So going to the first study, so this was a study conducted by researchers to evaluate the PFAS treatment at full-scale water treatment systems. So they compared the PFAS removal of various technologies across 15 drinking water treatment plants in the US. This table on the left summarizes the different technologies that they evaluated in these from this full-scale study. I'm not going to go through each one of them, but this technology includes these traditional treatment approaches like coagulation and flocculation systems. It includes even advanced oxidation processes. And of course, it includes granular activated carbon, ion exchange, and reverse osmosis to see which one performed ideally for removal of PFAS. So here we see the results for the removal of PFOA and PFOS in these various full-scale systems. In the figure on the right, what it shows is the removal as a fraction. Essentially, higher this number, higher the removal is. So 1 represents complete removal of PFAS. A negative value represents the concentration of PFAS in the effluent is higher than the initial concentration as such. So, and the various technologies are shown below, and they are categorized on the top. And as you can see, the coagulation and flocculation approaches and physical separation approaches are ineffective in treatment of PFAS. As you can see, the values are very low. Even the only system that shows some removal, about 49% removal, was a dissolved air flotation system, but that removal was just specific for PFOS, and other PFAS were not removed in that system. Microfiltration and ultrafiltration were not effective in treatment of PFAS. In some cases, especially for oxidation and chlorination system, we actually noticed this, the researchers actually noticed an increase in concentration of PFAS after treatment. And this was associated with transformation of precursors that might be happening in these systems, resulting in a higher concentration in the effluent. But if you look at the sequestration approaches, which is GAC, ion exchange, and reverse osmosis, the removal of PFAS were excellent. And any bars that's represented with a greater than sign represents concentration below detection limit in the treated effluent. Of course, there are some systems that did not perform ideally as expected, and we're going to talk more about it. So the lack of performance that was noticed for GAC and ion exchange is actually was explained very well by these researchers. The ion exchange system performed poorly because the system that was studied was not optimized for PFAS treatment in the first place. And it used like an upflow fluidized bed reactor setup, which is not a typical setup for ion exchange treatment of PFAS. And it is, as a result of this improper operation, the researchers concluded that PFAS was not removed by this ion exchange system. Granular activated carbon system at plant number 18 showed actually a higher concentration in the treated effluent for PFOS and PFOA. And this was as a result because the carbon material in this filtration system was very old. It was not reactivated or changed for years. And as a result, it was eluting out all the accumulated PFAS from the carbon, and the concentration was higher in the effluent. So this kind of suggested the importance of carbon replacement when treating PFAS. So this table is a summary of the removal of PFAS observed for other PFAS compounds in these different systems, more specifically on reverse osmosis, ion exchange, and granular activated carbon. Here I'm highlighting the PFAS compounds that are currently being considered for regulations in New York State. And as you can see from the result, reverse osmosis system performed excellent in the removal of all PFAS, in both short chain and long chain PFAS compounds. The greater than sign again represent concentration below detection limit in the treated effluent. In ion exchange resin treatment, long chain compounds were effectively removed, but only partial removal was observed for short chain compounds, as you can see in these numbers. Again, the reason here being that the ion exchange resin was not optimized or designed for PFAS treatment, but it was more focused for arsenic removal. So the system designed, or the EBCT or empty bed contact time, was used for arsenic removal rather than PFAS removal in the study. Granular activated carbon again performed really well for most of the PFAS compounds, except for the really short chain compounds like PFBA and PFHXA. Only partial removal was observed. The plant number 20 especially was a system that was specifically designed for the treatment of PFAS. And you can see like good removal of all PFAS, except for PFBA, which was the most challenging PFAS chemical to be removed by granular activated carbon. And this was due to its low hydrophobicity. PFBA is a very small molecule, so it's a short chain PFAS, and it exhibits very poor absorption onto carbon material. Here we see actually the breakthrough curves of like various PFAS in plant number 18, which is actually optimized for PFAS removal. This plant was designed as a lead lag design, meaning it had two columns in series of GAC filtration. The first column is called the lead column, and the second column is known as the lag column. The purpose of having such a design is when the lead column is exhausted, you still have as a backup column that can continue to operate to remove PFAS while the lead column is being replaced with a fresh carbon or with reactivated carbon. And I'd like to highlight a few important date here. This is a breakthrough curve. Again, it's C over C naught plotted with bed volumes. And the points highlighted here is the exchange of the lead lag column when the lead column is being replaced with fresh carbon, or both the reactive vessels are being replaced with carbon material. And clearly from these curves, breakthrough curves, you can see PFBA, concentration of PFBA in the effluent was very quick, within 2 months after operation of the GAC column. The breakthrough time for PFHXA and PFOA was about 10 months after the column was started. And you can see the time through breakthrough for PFHXA and PFOA was similar, but although complete breakthrough of PFHXA occurred fairly quickly compared to PFOA from this curve. PFOS showed the best removal in the system, and the breakthrough occurred only after 18 months of operation. And clearly you can see this was chain link dependent and also functional group dependent in the breakthrough curve. There was another study that also evaluated a full-scale treatment system for PFAS removal in Sweden. In this figure, you can see the concentration of PFAS in the y-axis and the various technologies evaluated in the x-axis. Similar to the previous US study, these researchers also found that the aeration and other filtration approaches like sand filters was not effective in the treatment of PFAS. As you can see, the concentration was still high in the treated effluent, but the granular activated carbon filtration was very effective in treating the various PFAS. And you can see different PFAS are shown and broken down here. Interestingly, what they noticed, the age of the carbon can also play an important role in the performance. The numbers above these bars represent the bed volumes processed by each of these GAC filters. The higher the numbers, the older the carbon, and then you can notice the higher the concentration of PFAS in the treated effluent. And interestingly, the concentration was higher for the short chain compounds because the breakthrough of short chain compounds was much earlier than the long chain compounds. The same study also conducted a long-term performance of PFAS in these systems, and they evaluated a 50% breakthrough time or bed volume for each of these compounds. And this is summarized in the table on the right. You can notice the short chain PFHXA had a quicker bed volume for breakthrough compared to the longer chain PFOA. Which exhibited at least 3 times higher in the bed volume process before the breakthrough occurred. So clearly the breakthrough was dependent on the chain length of the PFAS. And it was all the same trend was also observed for the sulfonic acids like PFBS, PFHXS, and PFOS, and where PFOS showed the highest bed volume treated before the breakthrough occurred, whereas PFBS showed the shortest bed volume for the breakthrough. Interestingly, if you can compare the sulfonic acid versus the carboxylic acid group, the sulfonic acid PFAS were retained much better in the granular activated carbon, which confirmed the previous studies that also evaluated and found the same result for these compounds. This study also evaluated the effect of empty bed contact time, or essentially the flow rate, on the performance of GAC filters in treatment of various PFAS. These figures represent, the left figure represent the removal efficiency for a new carbon filter, and the right figure represents the removal efficiency as a function of empty bed contact time for the old carbon filter. And as you can see, the removal efficiency was much better with higher empty bed contact time or lower flow rate. And this improvement in removal efficiency was significant for the old carbon compared to the new carbon. And the study concluded that the service life of the carbon material can be prolonged by almost half if the flow rate was decreased, and so that we can retain better PFAS in these systems. Moving on to the third study, this study actually evaluated a bench scale continuous column test to compare the performance of granular activated carbon and ion exchange for treatment of PFAS. They used a F400 Calgon material and Calris 2301 ion exchange resin for comparison purposes. And what the study found was the ion exchange resin performed better than GAC for both short chain and long chain PFAS removal. And similar to the other studies, the removal of PFOA was less than PFHXS and PFOS, suggesting that the sulfonic acid had greater affinity for removal in ion exchange resin. And again, the removal of PFHXS was lower than PFOS, and suggesting chain length dependent removal was also observed for ion exchange treatment of PFAS. This study actually performed an interesting cost analysis to compare the performance of GAC and the cost associated with GAC treatment and ion exchange treatment of PFAS. And for this analysis, they used PFOA and PFHXA as a model compound for short chain and long chain compound. And what the study found was that the ion exchange resin lasted 16 times longer than granular activated carbon for treatment of PFAS, meaning the activated carbon will have to be replaced 16 times quicker than the ion exchange resin to maintain the same treatment goals of PFAS. And overall, ion exchange treatment was found to be 20% less expensive than GAC, at least in the scenario that they analyzed. This is summarized really well in the figure on the left. The gray lines are the curves for the granular activated carbon treatment, and the dark black lines are the curves for the ion exchange treatment. And what this figure shows is the levelized media cost, that is the cost of media per treatment of unit volume of water versus the cost of the media itself. And as you can see, that although the cost of granular activated carbon as the media cost is much lower than ion exchange resin, the total treatment cost per unit volume for GAC is much higher for ion exchange treatment because it requires frequent change out due to exhaustion and early breakthrough of PFAS. The treatment goals can also play an important role on the cost. So here they analyze a scenario where the treatment goals could be either be a 50% of the short chain compound breakthrough or a 10% of short chain compound breakthrough. And what their analysis showed is there's a 200% increase in the cost for GAC treatment if the treatment goal was changed from 50% of for short chain compounds to a 10% breakthrough for short chain compounds for GAC. And a similar 100% increase was also observed for ion exchange treatment when the goal was changed from 50% to 10% breakthrough. So another study looked at the performance of different types of GACs in the treatment of PFAS. And in summary, what they found was the type of GAC did not matter much for the removal treatment of short chain PFAS. They performed similarly, but however, longer chain PFAS was retained better for F400 type and GAC 400 type, which is essentially a bituminous coal based GAC compared to a coconut shell GAC for long chain compounds. So the current understanding for early breakthrough of short chain PFAS. So as we already discussed, short chain compounds are exhibit lower hydrophobicity. So relative to long chain compounds, they are poorly absorbed onto your granular activated carbon. And this curve clearly summarizes that. So the bed volume for 50% breakthrough is the y-axis, and the partitioning coefficient is shown on the x-axis. And as you can see, it's a linear relationship where the short chain compounds are showing quicker breakthrough due to lower hydrophobicity, whereas long chain compounds show larger breakthrough volumes due to their higher hydrophobicity. The other reason why short chain PFAS can break through early from these filtration systems is due to competition between long chain and short chain compounds. The long chain compounds tend to block the absorption sites available in your filter media, so that the short chain compounds are not unavailable or do not have enough sites for them to absorb onto your media. And in some cases, even the absorbed short chain compounds can be displaced or replaced by your long chain compounds, and that can increase your concentration in your effluent, as observed in many of these studies. So going on to the next technology, which is reverse osmosis in nanofiltration. These are membrane separation technologies which rely on pressure-driven filtration process through selective membranes. As these are energy-intensive processes, so they're associated with considerable energy costs for large-scale applications. The different membrane treatment processes are summarized in the table left. They could be microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. And you can see the reverse osmosis pore size is the smallest, which is 0.1 to 0.7 nanometer in size, whereas the microfiltration have pore sizes larger than 1,000 nanometers. And this represents the size of the molecule that they can retain these membranes. And all these PFAS molecules have a size less than 1,000 Daltons. And as a result, nanofiltration and reverse osmosis are effective in treatment of PFAS and not membrane, micro and ultrafiltration systems. And this is a figure that shows like how various different membrane filtration can retain different components due to their size exclusion. mostly. So as we already observed in the previous studies, reverse osmosis are very effective in treating both short chain and long chain PFAS. And greater than 99% removal of PFAS was observed in both bench scale and full scale systems. But however, for reverse osmosis systems, in addition to energy being energy intensive, pre-treatment of water is very important. So you need to remove particulate matter and other interfering constituents that can affect the performance of reverse osmosis membranes. One of the important challenges of reverse osmosis systems is membrane fouling, which can occur due to presence of other organic matter and the growth of bacteria. And this could be a great, this could increase the O&M cost, and the water quality can influence the performance of our systems and treatment of PFAS. In a reverse osmosis system works a little different than the granular activated carbon and ion exchange system in that, like, the PFAS are absorbed onto your carbon and ion exchange resins, whereas in reverse osmosis system, they are rejected. So they are being concentrated in the waste discharge that's coming out of your reverse osmosis system. So in an RO system, you're then creating this concentrated PFAS waste that has to be managed further for treatment, either by treatment, permanent discharge, or safe disposal. Some of the common challenges with sequestration approaches is that the one main important challenge is PFAS are not destroyed by these techniques. They are rather phase transferred and accumulated in your carbon, your resin, or your reverse osmosis reject streams. Current practices are rely on incineration of these spent carbon and ion exchange resin to destroy your PFAS, but studies show that these are ineffective, and they actually release PFAS molecules into the atmosphere. And essentially PFAS are being reintroduced into the environment. So hence there is actually a need for destructive technologies to kind of break this forever cycle of PFAS being accumulated in your treatment systems and being discharged in other ways through either landfills or incinerations and so on. So looking at destructive technologies for PFAS, and as we already discussed, this carbon-fluorine bond energies are very high, and as a result, the PFAS molecules are highly stable, which means you really need very high energies or extreme conditions to break down the PFAS molecules. And this is actually explained really well in this figure on the right, which gives the comparison of electrical energy per order for various contaminants with PFAS. And electrical energy per order is defined as the amount of energy required to remove 90% of contaminant in a unit volume of water. So higher this value, more energy is needed to remove the same amount of contaminant. And as you can see, out of all these contaminants, the EEO for PFOA and PFOS is three orders of magnitude higher than these other common groundwater contaminants. That clearly shows like how stable these compounds and how much energy intensive these destructive technologies are for treatment of PFAS. There are several destructive technologies that are being studied and researched for PFAS destruction, but most of these technologies are in development stages. They've been evaluated at bench scale treatment of water. They show very limited pilot and full scale demonstrations. And some of the examples are actually shown in this figure on the right, which compares the EEO for various destructive technologies. And you can see it can span over a wide range depending on the type of PFAS you're treating. All these technologies have the characteristics of high energy consumption, low cost efficiency, and it requires extreme operating conditions like high temperature or extreme pH, and addition of excessive oxidants and so on. And another big challenge with destructive technology currently people are facing is there are unknown transformation of products after destruction. They are unable to close the mass balance on PFAS, which clearly demonstrate that there exist transformation products that we do not understand after treatment, and we do not know how toxic these transformation products are after treatment. So I'd like to highlight some of the ongoing work at Center for Clean Water Technology that looks at destructive technology of PFAS. So one of the technology that we are evaluating are electrochemical oxidation. It's a type of advanced oxidation process, but it uses electrical energy to induce reactions. The setup consists of a cathode, anode, and a working electrolyte. and a reduction happens in cathode and oxidation of contaminant happened on anode. So we are collaborating with a company called A-Clarity, who have a special anode material that's capable of degrading PFAS. And we have used an electrolyte of sodium sulfate to induce high conductivity to induce these reactions. Two types of oxidation can occur in the anode material. You could have direct oxidation of PFAS, where PFAS can come into contact with the anode and get destroyed. Or you have a mediator that produces an oxidant, and that the oxidant can react with PFAS to break them down. And some preliminary data to show that this system is actually effective in treatment of PFAS. So we observe good removal of PFOS, which is the orange curve, and PFOA. And this plot is essentially C over C naught with time. But we saw only limited removal for the short chain compound PFBS. And from this data, we understand that direct oxidation is the main pathway by which PFAS is being degraded using the electrochemical oxidation system. And as you can see, because PFBS has a poor sorption coefficient, as a result, it did not come into contact with the anode material for it to be destroyed. The other approach that we are working for destructive removal of PFAS is electron beam irradiation treatment. Here we are collaborating with Fermi National Accelerator Lab. It's an advanced oxidation reduction processes. The electron beam water radiolysis can generate reactive species such as aqueous electrons and hydroxyl radicals that can react with your PFAS molecules to break them down. Again, like other destructive technologies, they need extreme conditions. We notice that we require low dissolved oxygen and very high pH to induce such reactions. But successful degradation of a wide suite of PFAS was observed in our study. And as to summarize, this is a degradation of various types of PFAS at 250 kilogray of dose applied in the E-beam treatment process. As you can see, most of these PFAS showed good removal, about 80 to 100, even 100% removal at 250 kilogray. But short chain compounds, similar to your electrochemical oxidation, showed resistance to degradation. But when we increased the dose to 1000 kilogray by 4 times, we did see good removal for these short chain compounds, which kind of suggests that short chain compounds are less reactive compared to the long chain analogs. And they could be more persistent in the sense because of their stability. So from all these studies, what we kind of realized now that there is no one proper technology that can treat and destroy PFAS, but we might need a treatment train or a combination of technologies to achieve the treatment goals. A study did a critical review and looked at a combination of various technologies and efficiency to remove PFAS, which is summarized in this table on the right. And as you can see, it could be a tandem treatment train, whereas you apply a sequestration approach followed by a destructive treatment approach to achieve your treatment goals. And about 90% removal or even 99% removal have been achieved by using different combination of treatment. Or it could also be a parallel treatment where you combine 2 different technologies at the same time to achieve the treatment goals that you're aiming for. But again, all these combination of technologies are at development stage. They've been tested only in bench scale approaches, and more research is needed to understand what's the efficacy and cost associated with it. And also it's going to vary depending on the applications we are targeting for PFAS removal or remediation. So in summary, the stability and surfactant nature of PFAS makes many treatment technologies ineffective. So even the aggressive technologies like advanced oxidations and thermal treatment that works well for most of the contaminants do not work well for PFAS, and they require extreme conditions like high temperatures or high chemical doses and extreme pH to break them down. However, now in existing technologies, sequestration approaches are the most effective ones in treating most of the PFAS. These include granular activated carbon and ion exchange treatment and reverse osmosis. Short chain compounds showed quicker breakthrough than long chain compounds for both granular activated carbon and ion exchange treatment systems. Ion exchange treatment performed better than GAC in both cases because of its dual action of both hydrophobic interaction and electrostatic interaction of PFAS molecules. For GAC treatment, it was shown that carbon change out is expected to be more frequent if you're going to aim to treat short chain PFAS. And typically a lead lag design is required, or a combination of even GAC and ion exchange resin may be needed to achieve the treatment goals for short chain compounds. Sequestration approaches, however, do not degrade PFAS. They create this concentrated PFAS waste stream that has to be disposed of safely. And that's the reason we are, like, more research is focused on developing destructive approaches for the treatment of PFAS, but most of the destructive approaches are in the development stages and more research is needed. And one of the important challenges with destructive approaches is inability to close the PFAS mass balance, which indicates a production of unknown transformation products, which are also organofluorine compounds. It could be PFAS, but we don't know how toxic these chemicals are. So without that knowledge, it's difficult to implement these technologies for full-scale treatment of PFAS. But from these studies, it's clear that a treatment train or combination of sequestration and destructive approaches are actually needed to remove and destroy PFAS to achieve treatment goals. With that, thank you for your attention. I'd like to acknowledge a few people from the center who worked on these projects, like Kaushik Lande is working on the electron beam and electrochemical oxidation systems. Postdocs Yi Zhang, Cheng-Xuan Li, and Amit Maroli are supportive of all the other projects. I'd like to thank the Center for Clean Water Technology team and the funding sources for some of the projects that we're working on related to PFAS, which is the New York State Department of Health. And with that, I'll be happy to answer any questions you may have. If you have any questions, feel free to post them on the chat box, or you can unmute yourself and ask the questions in person as well. Thank you for your attention. So do we have any questions? All right. If there are no other questions, but again, you can see our contact information on the slide. Feel free to reach out to us if you have other questions or comments on this presentation. This presentation will also be made available on YouTube after the recording is done. Wish you all a very happy New Year and have a very nice day and the rest of the year. Thank you all.